guidance of John Preskel in 2018, right? Okay. She won the Ilya Prigozhin dissertation award, which is given every 2 years to someone whose thesis is on thermodynamics. It's very prestigious, every 2 years. It's been awarded since 2001, if I remember correctly. So she's in a very elite group. After graduating from Caltech, she went on to Harvard for a postdoc, and now, like I said, is at NIST. So just a couple things I thought I'd make a connection, because I also went to Caltech, got my PhD at Caltech. I started almost 30 years ago to the day. So in 1992, I started at Caltech. And I remember going to talk to John Preskel. And if you don't know John, he's an extremely deep thinker. He's unbelievably smart. He was known, and the reason he was a professor at Caltech was for his work on monopoles and cosmology, the monopoles from breaking gauge theories down, and then the cosmological implications of that, and on black hole physics. He had done a lot of work on black hole and basically quantum information in black holes. So there's a connection with what his more recent work is about. And I went to talk to him and was asking him what he was working on. And he was saying, he's been working on black holes, but this guy, Peter Shor, just came out with this new thing, and he was very excited about it. And if you know what happened, he totally switched his research and has been doing quantum computing, quantum information since that time. So I was not smart enough to jump on the bandwagon at that time, but obviously Nicole was smarter than I was. The other thing about John is he gives the beautiful lectures with unbelievably good analogies, so much so that you go to his lecture, you figure you know it exactly right. And I don't know if it was by John's teaching or it's innate in Nicole, but if you read her book, you can see that she also has the skill of using analogies and explaining things very clearly. So her talk is Quantum Steampunk, the Physics of Yesterday's Tomorrow. She coined the term, I think in your thesis for the first time or right around then, which is the idea that you're combining thermodynamics, which is really an old science in some sense, with the new science of quantum information science, So please welcome Nicole.
Thank you for the very kind introduction, and especially, right? Thank you. You can tell I'm a theorist. I'm not the one who deals with the technology. So especially thank you for the kind comparison with John. I don't know if I'll live up to it, but I'll certainly try to. And finally, thanks very much for the invitation to speak here. And especially thanks to all of you who've made it to almost the last event of the conference. So I spent a year studying physics here. If this will work. No, it did a moment ago. That's all right. I spent a year studying physics here, in a place that some of you will probably recognize, in Waterloo, which is a city near Toronto. The Waterloo excels in theoretical physics, tech startups, and winter. Lots and lots of winter. But eventually the winter ends, and one day in the spring for a study break, I visited the Waterloo Public Library. So there I found this novel by the Canadian poet J. Ruszewski, The Wolfsenberg Clock. One scene takes place in Austria during the 1800s. An inventor is standing at a balcony, gazing down on the ballroom below, which he's converted into a workshop. He and his family members build automata, the clockwork-driven elephants and snakes and so on. So this inventor is standing on this balcony, gazing down on his miraculous creations with his overcoat trailing out behind him. And the atmosphere is just palpable. It was shortly after that I learned I'd encountered steampunk. Steampunk is a genre of literature, art, and film. Steampunk stories take place during the Victorian era, when the Industrial Revolution has been humming. Some of the earliest factories are belching smoke into the air. London is full of smog and Sherlock Holmesian mysteries. Railroads are cutting across the American West for the first time. And there are people wearing top hats and waistcoats and petticoats. Against this backdrop are futuristic technologies, automata, time machines, flying ships, and submarines. Another Canadian poet, Douglas Featherling, has supposedly said, "Steampunk is a genre that imagines how different the past might have been had the future come earlier." You might have encountered this steampunk novel, The Time Machine by H.G. Wells. It was one of the first steampunk works, as it was written during the 1800s. But steampunk is very much with us still. The Invention of Hugo Cabret was a New York Times bestseller in the early 2000s. Enola Holmes was one of the first films released on Netflix due to the pandemic. It's about Sherlock Holmes's little sister, Enola. So the film was a hit, I loved it, and the sequel is coming out in November. The Nevers is a show on HBO about Victorian women who have supernatural gifts. These works reach back to the past and ahead to the future. This fusion of old and new creates a wonderful sense of nostalgia and adventure, romance and exploration. So fans dress up in steampunk costumes with top hats and goggles and gears and gather at steampunk conventions for the sake of a fantasy. But someone is requesting a live transcript. Should I enable? Okay. Maybe. Let's try now. No, okay. Okay. If people here won't get too distracted. So people gather at these steampunk conventions, all dressed up for the sake of a fantasy. But I argue this fantasy is becoming a reality in my field of research. I'm a theoretical physicist at the intersection of quantum information and thermodynamics. So probably many people here studied thermodynamics in core physics or engineering or chemistry courses, but I found that scientists often don't quite remember what thermodynamics is, and many students never learn why we should care about thermodynamics. Thermodynamics is the study of energy, plain and simple. It was developed during the Victorian era to describe one of the transformative technologies of the era, the steam engine. Today's transformative technologies include quantum devices, which are very, very different. They're not macroscopically large. In fact, the thermodynamic limit contains infinitely many particles. Our technologies can have coherences relative to the energy eigenbasis, and they can have entanglement and other non-classical properties. Sure, quantum statistical mechanics has been around for decades, but statistical mechanics has a different flavor than thermodynamics. Statistical mechanics primarily focuses on the calculation of partition functions. Thermodynamics is, like information theory, an operational theory. Using an operational theory, we reason about agents who need to perform certain tasks given certain resources. We figure out how efficiently the agents can perform these tasks. An operational task in information theory is data compression. Suppose that I want to send you a message. How much can I squeeze the message down? How large a memory do I need? An operational task in thermodynamics is turning a jet propeller. How much energy do we need to turn the propeller at a given speed? Thermodynamics focuses on efficiency, work, and machines, such as engines. Today, we need to ask how quantum engines would look and what they could achieve. We need to re-envision the thermodynamics of the 1800s for the 21st century. Again, we need to reach back to the past and ahead to the future. Given how thermodynamics shares its operationalism with information theory, it's no wonder that quantum information science is revolutionizing thermodynamics. This resulting fusion of old and new, I call quantum steampunk. So a genre of science fiction is coming to life at the intersection of quantum information science and thermodynamics. I'll briefly review a little information theory, a little bit of quantum physics, and a little thermodynamics. Many of you will know some of this material, but different people here have different backgrounds. And also, it'll be useful to have in mind certain perspectives so that we can recognize them later in a thermodynamic application. By information science, I mean the study of how efficiently we can perform information processing tasks. These include solving computational problems, such as calculating a satellite's trajectory, communicating information, such as via the web, securing information cryptographically, and storing information in memories. Fundamentally, information is basically the ability to distinguish between alternatives. Say that a friend asks you whether the pub down the street, in Victorian London, of course, is open or closed. You peer through the window and see either foaming mugs or cleaned mugs sitting upside down on the counter. You've gained the ability to distinguish whether the pub is open or closed. So you gained information. We measure units or information in units of bits, at least if we were raised by computer scientists. Thermodynamicists prefer units of nats, but I will not subject you to those. The bit is the amount of information we gain if we have no idea of the answer to a yes or no question and we learn the answer. Say that when your friend asks about the pub has a probability 1/2 of being open and a probability 1/2 of being closed. When you peer through the window, you learn a bit of information. But I'm going to review one perspective on quantum theory, on entanglement in particular, to lay the groundwork for a thermodynamic application. Imagine that some young physicist, let's call her Audrey, has a spin 1/2 particle and her brother Baxter has another. The siblings can perform some operation on their particles that creates entanglement between them. By the way, this illustration is by Todd Cahill, as are other black and white drawings that we have seen and that we will see in this talk. So Todd is a steampunk artist. He illustrated my book. He had no experience with quantum physics whatsoever, so the process was an adventure, but he succeeded, I think, in making very imaginative illustrations. Suppose that Audrey measures whether her spin is pointing upward or downward. I'll label the possible outcomes by 1 and 0. If the two particles are entangled maximally, then she has no idea which outcome she'll obtain. 1 and 0 have 50-50 chances. Now, suppose that Audrey measures her particle and Baxter measures his identically. Then the two siblings can predict something about the joint outcome. If Audrey obtains a 1, for example, in the case of a singlet, she'll know that Baxter will obtain a 0. And if she obtains a 0, she knows that Baxter will obtain a 1. Furthermore, there is a measurement that the siblings can perform jointly on the pair of particles together, such that they can predict the outcome with certainty in advance. So And of course, that measurement is a Bell measurement. So there's some information that isn't in Audrey's particle, it isn't in Baxter's particle, and it isn't in the sum of the two particles addressed independently. It's spread across the pair. But when it comes to entanglement, the whole really is greater than the sum of its parts. But many of us here leverage entanglement in quantum information science. By quantum information science, I mean the study of how we can use quantum phenomena to process information in ways forbidden for classical systems. I am, as a thermodynamicist, obliged to point out that one of the most ambitious potential applications of quantum computers is to energy use. But Microsoft's quantum team detailed this idea. In some countries, food security is at crisis levels, especially today. In other countries, food security is at some of the highest levels ever in history. So fertilizer is extremely important across the globe. We invest about 3% of the world's entire energy output on fertilizer production. Why do we spend so much energy? Because we produce fertilizer using an old technique from 1909. Bacteria can accomplish this goal much more efficiently. But those bacteria use a molecule that's too complicated for us to simulate on classical computers. The molecule, though, is quantum. So a quantum computer will naturally be better suited to unlocking the molecule's secrets. And if all goes as hoped, and that is a very big if, then transforming fertilizer production into energy use. But this potential application and many others help account for how governments and companies are pouring funds into quantum research, technology, and education. Speaking of companies, this object belongs to IBM. I think we might have seen exactly this photo in an earlier talk here, because it is a very beautiful photo. And granted, Google, Amazon, and others have similar devices, but this is a very compelling photo that is very easy to find on Google Images. So this is a dilution refrigerator, as some of you will know, colloquially known as a fridge. It's not a quantum computer, despite what we sometimes see in the media, even though it looks cool enough to be one. Actually, many people think it looks steampunk because of the gold and copper and wires sticking out everywhere. So this object holds a quantum computer formed from superconducting qubits, which fit on a small chip. The chip needs to be at low temperatures to support quantum phenomena such as entanglement. So the fridge cools the quantum computer to tens of millikelvin. Actually, once earlier in the pandemic, I was collaborating with some superconducting qubit experimentalists. We were wrapping up a project, and my husband, who is a classical computer scientist, heard me zooming about this fridge, and he became a little indignant. He said, "This device cools things down to below the temperature of outer space, and you couldn't even call it a freezer." Anyway, cooling leads us to the third element of our triumvirate, thermodynamics. Thermodynamics was developed during the 1800s. It is the study of energy, the forms that energy can be in, and the transformations amongst those forms. Objects can transmit energy in two forms: heat and work. Heat is the uncoordinated energy of particles jiggling about randomly. Heat is disorganized energy and so isn't directly useful. Work is coordinated energy that can be directly harnessed to power a factory or charge a battery or raise an anchor. Heat engines convert random heat into coordinated work. Heat engines powered the Industrial Revolution by powering factories for the first time. Around that era, people started wanting to know how efficiently engines could operate. So they developed the theory of thermodynamics, and they gave it a practical bent. However, the practical questions led to fundamental questions, such as why does time flow in only one direction? And do materials really consist of particles too small for us to see? So the theory of atomism had not been entirely accepted by the Victorian era. Cooling, expelling heat, is a thermodynamic process. But how do you measure the heat emitted by a quantum system that's cooling? You can measure the heat emitted by a classical system by measuring the energy, cooling the system, and measuring the energy again. The initial energy minus the final energy is the heat lost. But quantum systems are more delicate than classical systems. Heisenberg intuited that if you measure a quantum system, you disturb it. Robertson codified this intuition in 1929 in the uncertainty relation we learn as undergraduates. Thanks to uncertainty, if you measure a quantum system's energy, you probably change the energy. If you try to measure the heat absorbed by a quantum system, you probably change the amount of heat absorbed. So how we can measure heat or even conceive of quantum heat is not straightforward. Furthermore, this fridge is a large classical system. What if we tried to build a fridge from a quantum system? Could we? How small could we make it? Could quantum phenomena such as entanglement benefit a quantum fridge as they benefit quantum computers? More generally, just as there are information processing tasks, such as encrypting information, there are thermodynamic tasks, such as refrigerating and powering cars and charging batteries. Given that quantum phenomena benefit information processing tasks, can they benefit thermodynamic tasks? How can we extend the Victorian theory of thermodynamics from large classical systems, such as steam engines, to small quantum and information processing systems? These questions underpin quantum thermodynamics, my field of research. I believe that this field shares its aesthetic, its spirit with steampunk, hence the name. How and when did quantum thermodynamics develop? The field has roots that stretch back to the 1930s. Right after quantum theory was formulated, people began wondering whether it could explain thermodynamic phenomena. During the 1950s and 60s, researchers designed the first quantum engine. It consists of one atom, which you can use in a maser. Many people here will know that a maser is like a laser, shown here in its all-important task of driving a cat insane. However, whereas a laser emits visible light, a maser emits microwave radiation. The atom's energy level has 3 populated levels, 0, 1, and 2. So it has 3 energy gaps, 0, 1, 1, 2, and 0, 2. Each gap can exchange energy with a heat bath or large environment or reservoir, but I really like thinking of these more as baths, whose frequency is filtered. The one bath is cold, one bath can have a negative temperature, and one bath can have an infinite temperature. By negative temperature, I mean in Kelvin, not the negative Fahrenheit or the negative Celsius temperatures that I experienced in Waterloo, Canada for so long. We learned in statistical physics class that negative temperatures are accessible to systems that have finite state spaces, such as a collection of spin 1/2 particles. Temperature is the rate of change of energy with the entropy at a fixed volume and number of particles and so on. Or equivalently, the inverse temperature is how quickly the entropy grows as the energy grows. Entropy is a measure of how big the state space is that is accessible to the system. Consider a system of spins in an external magnetic field. When all the spins align with the field, the system has its lowest energy. Only one such configuration exists. The entropy is minimized. If all the spins except one align with the field, then the system has a greater energy. Also, the number of configurations is greater. It's the number of spins that you can choose to be the one pointing downward. As the energy grew, the entropy grew. So the inverse temperature is positive. If all spins but two align, the system has a greater energy and a greater entropy, as the number of ways you can choose 2 spins from 6 to point downward is greater. This trend continues until half the spins point downward. The number of ways you can choose 3 spins from 6 maximizes the entropy. Then, as the energy increases further, the number of configurations decreases back down to the number of ways that you can choose just 2 spins from 6. The entropy decreases, so the inverse temperature is negative, so the temperature is negative. This negative temperature system has lots of energy, so negative temperature systems are very hot. So the negative temperature bath gives the atom energy, pushing it upward onto the top level. Also, the cold bath drops some probability weight of the quantum state onto the lowest level. The imbalance between the weights is eliminated by the infinite temperature bath, into which the atom emits energy. How come? An infinite temperature system has its weights spread equally across the accessible energy levels. Moreover, the infinite temperature bath, upon accepting this energy from the atom, produces no entropy. The entropy produced is the energy accepted by the bath divided by its temperature. As the temperature diverges, the entropy vanishes. Producing no entropy, no waste and disorder, the energy emitted by the atom serves as work. But it turns out an engine doesn't need gears and cogs and other moving pieces. It can consist of just one atom. Moreover, the engine takes advantage of how quantum heat baths can have negative temperatures and so be especially hot. Henry Scoville and collaborators at Bell Labs designed this quantum engine between 1959 and 1967. Since then, quantum engines have been designed to take advantage of quantum phases of matter and quantum harmonic oscillators and squeezed state baths. So there are lots of options now. But back to our historical tour. Over the decades after the first quantum engine was designed, quantum thermodynamics had a small following. It wasn't seen as a discipline. Some people even said that quantum thermodynamics was an oxymoron. Thermodynamics was developed to describe large classical systems such as steam engines, so thermodynamics couldn't possibly have anything to say about quantum systems. However, over the past decade, quantum thermodynamics has experienced a boom. Here's a photo from my community's big annual conference back in 2018. We met in Santa Barbara. That's why the scenery is gorgeous. We form an international community with hotspots in the United Kingdom, Germany, Israel, Brazil, Switzerland, and elsewhere. A few of us quantum thermodynamicists work in the United States. The US broadly is starting to catch on. Colleagues in many-body physics, high-energy physics, and more are starting to incorporate quantum thermodynamics as a new twist into conferences, grant proposals, and research programs. Last year, the APS March meeting featured multiple quantum thermodynamics sessions. In fact, colleagues and I are establishing North America's first quantum thermodynamics hub this month. You're actually seeing a sneak preview of the official announcement will probably be next week. We aim to become the local watering hole for those curious about quantum thermodynamics, airing their best quantum thermodynamics results, and creating a community across North America and connecting to the rest of the world. Why has quantum thermodynamics been booming across the world? Quantum information science matured in the early 2000s. It came to offer mathematical and conceptual toolkits for understanding quantum systems through how they store and process information. Quantum information science also came to offer unprecedented experimental opportunities. Labs achieved exquisite control over tens to hundreds of thousands of atoms and ions. We're using all of these tools of quantum information science to build and test a theory of quantum thermodynamics. Here's an example. We'll start with a classical story that showcases the interplay between information and energy. Then we'll see what quantum physics adds. We can store a bit of information not only in, say, a transistor, but also in a gas particle in a box. Suppose that this particle is classical, like a miniature basketball. It's a really, really simple ideal gas. If the gas is on the box's right-hand side, we'll say that it encodes a 1. If the gas is on the left-hand side, we'll say that it encodes a 0. Suppose that we have no idea where the particle is.
All right, where's the cup?
It can be anywhere in the box.
Ouch. Dry
Its
off.
position is totally random. Suppose that we want to reset the particle's position to the box's right-hand side. So a nice, clean state. This is like taking a messy sheet of scrap paper that's been scribbled on randomly and erasing it to a nice, clean state. To erase the bits encoded by the gas, we let the gas exchange heat with its surroundings, which have a fixed temperature, through the box's walls. We slide a partition into the box near the left-hand wall and push the partition to the box's center. The gas ends up trapped in the box's right-hand side. At what cost? We have to compress the gas, so we have to exert energy, namely work, the coordinated, useful sort of energy that can be transferred between systems. The minimum amount of work required is Boltzmann's constant times the temperature times log 2. So we spend work to reset the particle's position or to erase the bit of information that the gas encodes. In other words, erasure, an information processing task, costs work, which is a thermodynamic resource. What's more, suppose that we want to compute and compute and compute and compute. Eventually, we'll run out of scrap paper. The universe doesn't contain an infinite supply of scrap paper, so we'll have to erase some. We just saw that erasure costs thermodynamic work. So computation has an intrinsic thermodynamic cost. When I first learned that in my first quantum computing class, senior spring of college, I was staggered because a priori, information and energy seem not necessarily to have anything to do with each other, but they turn out to be inextricably bound up. Rolf Landauer, an information scientist at IBM, figured this out in 1961. The process that we just saw is called Landauer Erasure. You might know Landauer better as a skeptic of quantum computing. People at this conference are trying to prove him wrong about whether quantum computers can work, but he does seem to have been right about the role of work in quantum computing and information processing more generally. But what happens if we add quantum physics to this mix of information and energy? The story can change in many different ways. I'll share one way discovered by colleagues of mine, including the Portuguese physicist Lydia Del Rio. Suppose that we want to erase not a classical bit of information, but a qubit. We can encode a qubit in Audrey's spin 1/2 particle from a few minutes ago. Audrey's qubit can be entangled with Baxter's qubit, again in some fixed temperature environment. We said that if Audrey's qubit is maximally entangled with Baxter's, and Audrey measures her qubits, then she has no idea whether she'll obtain a 1 or a 0. The outcome is totally random. So Audrey's qubit resembles the gas particle bit whose location, right or left, 1 or 0, is totally random. Just as we could erase the gas particle bit, Audrey can erase her qubit or reset it to the 0 state. My colleagues showed that Audrey can erase her qubits while gaining work that she can use to charge a battery or lift a tiny weight. This result should surprise us. Landauer said that we have to spend work to erase information. The trick is to sort of burn the correlations between the qubits. Entanglement serves as a kind of thermodynamic fuel together with heat. So quantum phenomena, such as entanglement, can serve as resources in thermodynamics, in work extraction, as in information processing, as in computing. By the way, Pittsburgh really is a perfect place to give a talk about quantum steampunk. For example, this steam engine replica is a 15-minute walk away in the Phipps Conservatory, which was founded during the Victorian era and even has a Victoria room. This is so perfect, I could not have made it up. So thank you for the opportunity. Beyond erasing information, we can build quantum thermodynamic engines, refrigerators, ratchets, and batteries. Quantum phenomena can benefit such devices, my community has found. We can use entanglement as a resource in refrigeration. We can charge quantum batteries at a greater power if we entangle them than if we don't. A quantum engine that, so to speak, burns information can perform more work on average than its classical counterpart. And quantum engines can operate under conditions in parameter regimes in which classical engines cannot. These results not only help us extend Victorian thermodynamics into the 21st century, but also help us understand better where the quantum world differs from the classical. If we gaze into the future of quantum steampunk, what do we see? This field has been gaining momentum and participation sight unseen over the past decade. I expect the field to continue this upswing and increasingly join the ranks of established fields of physics, such as astrophysics and elementary particle physics, and as of a few years ago, because of places like the PQI, quantum information science. Some of us quantum thermodynamicists are building bridges to long-established fields of physics, just as quantum information science has offered a new lens onto other fields, such as thermodynamics, we're now using quantum thermodynamics as a toolkit to understand black holes and chemistry and more anew. So first, grand opportunity is to expand quantum thermodynamics far beyond its original boundaries. Second, quantum thermodynamics has its roots in theory. From quantum thermodynamics, we've gained fundamental insights about what it means for time to flow, what divides the classical realm from the quantum, and more. But quantum thermodynamics is growing increasingly experimental. Experiments are testing the theory and sparking new theory. Personally, as a physicist, I've collaborated with 4 quantum labs over the past 2 years. One uses photons, one uses ions, and 2 use superconducting qubits. We have lots of options, and I expect the community increasingly to take advantage of them. Most of the experiments happening now are proof of principle. They show that we can operate a quantum engine if we try very hard, but those engines perform less work than we have to invest in cooling the engines down and manipulating them. So a third opportunity is to make quantum thermodynamics practical. The original theory of thermodynamics went hand in hand with the Industrial Revolution, which was eminently practical. Quantum thermodynamics should go hand in hand with similar utility. For example, I'm working with experimentalists in Sweden on a quantum refrigerator for cooling quantum computers. Suppose that the quantum computer inside this classical refrigerator has just finished a computation. Its qubits are used up. To reset the qubits, we have to cool them even more. We can put a quantum refrigerator inside the classical refrigerator to reset the qubits. The experimental test of our theory is actually taking place now at Chalmers University in Sweden. Quantum thermodynamics is an incredibly exciting, dynamic, emerging field. It's vibrant and growing. It offers both fundamental insights and technological possibilities. If you'd like to learn more from my book, then you can obtain a discount using this code if you order directly from Johns Hopkins University Press. When I was a master's student back in Waterloo, I read about steampunk in a novel. But this genre of fiction is really coming to life at the intersection of quantum information and thermodynamics. But fantasy is becoming a reality. Thank you.
Thank you very much for that lovely talk. I'm trying to get this to go on. It's not working. Without this, I think. Oh, there goes. Hello, hello. Good. Questions?
Wonderful talk. I'm curious when the first quantum steampunk novel is going to come out. Are you writing one?
I have been asked about that. I'll say that if any literary agents read this book and would like to propose that I write a book proposal for a steampunk novel, quantum steampunk novel, then I would be interested in hearing from them what they have to say. I can also add that we are going to be taking steps to try to encourage the growth of quantum steampunk literature. The Quantum Thermodynamics Hub that I mentioned this academic year is going to be hosting a quantum steampunk short story contest. We have a really amazing slate of judges lined up, including Ken Liu, whom some of you might know, he's a really incredible science fiction and fantasy writer. There are going to be several thousands of dollars in prizes. So again, this is a sneak preview, but hopefully a wave is coming.
A quick follow-up about your quantum refrigerator, if I may. Can't I simply wait for the qubit to reset in a quantum computer versus in, I don't know, for a gas? Like, you know, I'm not sure what, because the state space for a gas atom might be bigger. And whereas for a quantum computer, it's just 0 to 1, right? Or 1 to 0, whichever way it goes. Do you really need a quantum refrigerator for that?
The idea is that using this quantum refrigerator, we can get the superconducting qubit to be colder than it would be if it just thermalized to its environment, which is already pretty cold. It's in the center of a dilution refrigerator, but we can do even better using a quantum refrigerator.
Thank you.
Thank you. I was wondering if there are anything known about connections with some of the quantum ideas that have been coming up in biology recently. I mean, the structure of the discourse there seems a bit similar. For a long time, everyone's thinking biological systems are so warm and wet that they're bound to be so decohered that everything there is going to be effectively classical. That turns out to be wrong. We don't quite know why it's wrong, but we're seeing lots of things of that kind going on. Let me just leave that open and ask if there's been any interesting connection to some of the experimental stuff that's come out of there.
There is some overlap. I can give an example. I had the privilege and pleasure of working with a chemist at UC Berkeley, David Limmer. He works with, he's a theorist, so he doesn't work in the lab with, but he works theoretically with photoisomers. These are molecular switches. They appear very broadly across nature. For instance, they're in our eyes and in technologies. One can fabricate them. But these are quantum systems. They're far from equilibrium, and they undergo non-adiabatic processes, but they are in biological systems. If they absorb a photon, then they have the opportunity to switch from one configuration to another configuration. He was interested in deriving a sort of general thermodynamic style bound on the probability that one of these molecular switches would switch. We found that we can use a tool from quantum thermodynamics, resource theory, and some results within the resource theory framework in order to derive his bound. So that's one example.
Wonderful talk. Can you repeat again how erosion of the information takes energy with that box example?
I didn't quite hear everything.
Oh, sorry. I was a bit lost when you were talking about the erasure of the information consumes the energies. Can you using that box example to detail on that again?
So is the question to review how information is
Like how erasure of the information takes energy?
okay, so how erasure requires energy.
Yeah.
Yes. So I gave one example, and if you want to accept the Landauer principle that erasure more generally in other platforms and via other protocols also requires at least this minimum amount of work, then we need a more general arguments. But for the sake of simplicity, I'll stick for the moment with a simple example. So in the case of this gas in a box, imagine that we start out not knowing where the gas is. Again, the gas can encode information through its position. So imagine that we've performed a computation. We have decided to use a really weird computer whose memory consists of gases and boxes. So we just finished up this computation. The bits, so the gases and boxes are in whatever strange states they were in at the result of the computation. We don't really care about what the result was. Maybe we did the computation yesterday. We forgot what the result was. We just want to reset our bits of information so that all of the particles are in their ready states so that they can encode new information. We can perform a new computation. so that we can use these gases and boxes as clean bits akin to clean scrap paper on which we can perform our next calculation. Then via the protocol I just described, we can accomplish our goal of resetting every single bit to having the gas in the right-hand side of the box. We can reset every bit to its clean 0 state, or I think I called it a 1 state actually, by compressing the gas. And we know from basic chemistry or physics that in order to compress a gas, we have to spend work. So that's how we have to spend work in order to get rid of the results of the old computation from yesterday.
My question is about, so if entanglement can, make you, if entanglement can give you work in erasing information, what is the thermodynamic cost of creating entanglement? Is there a notion for that?
It depends on what framework we're using. So what you have available to you. Again, I like to think of thermodynamics as an operational theory. We'll often state a problem in terms of an agent who starts out with certain resources and is assumed to be able to do certain things and not do other things. For instance, thermodynamic agents cannot break the first law of thermodynamics, energy conservation. So in the example that I gave, our agents was just handed at the outset, so he or she or whoever it is has as a resource entanglement. Then if you want to say, well, suppose that we want for our agents to create entanglement, then, and what would that creation cost? Then we should also specify what can our agent do, what can our agent not do, and what do they start out with? So the answer will depend on that. The one framework for choosing what the agent starts out with and can do and cannot do in thermodynamics is a thermodynamic resource theory. And using that, you can calculate via an entropic function the minimal cost of preparing your favorite state. Depending, if you're creating an entangled state, then the work cost will depend on both the state and also the Hamiltonian governing the qubits that are in this state.
Any other questions? Okay, if not, oh, yes, we do.
I just wanted to ask a bit about the comment you made about the flow of time in this framework. And I mean, the thought I had was, I mean, in statistical mechanics, you can relatively clearly see where you might be getting some sense of an emergent flow of time, because you've got dynamical processes that humans don't care about, that just do their own thing. You know, water goes downhill whether or not we put it at the top in the first place. You can macroscopic dynamical equations have, you know, clear time reversal asymmetry. In thermodynamics as a resource theory, I mean, my kind of initial thought would just be, well, simply formulating it that way with the external intervener and the intervener's external choice of operations to imply kind of looks as if you put time reversal asymmetry into the theory at the outset. So I'm sort of interested what the route is to get some kind of insight into the direction of time in that kind of framework.
Okay, yes, I think of resource theory as indeed one of the frameworks within thermodynamics that has dealt a lot with the second law of thermodynamics. And so we could say the arrow of time, fluctuation relations are another alternative. I think of the second law of thermodynamics as linked to understanding why time flows in one direction and being able to be phrased in terms of a spontaneous process. Suppose that you have a closed isolated system, or to go back to our example of a gas in a box that exchanges heat with its surroundings, suppose that the gas is in some initial macro states. We have in mind some other macro states. We ask, under what condition can this macro state turn into that process or turn into that macro state spontaneously? To answer that question, if the system technically is thermodynamically large and the initial and final states we have in mind are equilibrium states, Then we identify the relevant free energy, which in this case is the Helmholtz free energy. We asked, does the free energy decline monotonically over the course of this process we have in mind? If so, then yes, the process can happen spontaneously, and the process is happening spontaneously sort of goes along with the flow of time, at least in the way I think of it. We could generalize this setting and this question. We could say, suppose that I have a system that could be quantum. It could be small instead of thermodynamically large. The initial and final states don't have to be equilibrium states. If I'm just interested in one quantum system in some state, turning into another quantum system or in another state via some process that we think is in line with thermodynamics, obeys energy conservation, and so on, under what condition can that process happen? Since the question is more general, we have to do more mathematical legwork. We have to check a whole set of inequalities. But I think of the set of inequalities as kind of fine-graining the conventional second law.
Any other questions? All right. If not, let's thank Nicole again for a beautiful talk. And that is the end of all the talks for the PQI conference. Nicole has graciously agreed to stick around and sign books if you happen to have a copy. If not, you can come up and say hi. I'm sure she would love that too. We also have some lab tours. And if you haven't signed up, you can still go on them. So please do so if you so choose. And if and that's pretty much it. Thank you all for coming to PQI 2022. We look forward to seeing you all again throughout the year and at the event next time. All right, thank you.